Welcome to lecture B17. We're moving now in this lecture to chapter 25, and in particular, we're in section 25.2, where we talk about estimation of parameters. And in this lecture, we will learn about the maximum likelihood method for estimating parameters. And this method is actually, once you get the hang of it, I think it's pretty simple. And it follows a recipe that goes like this. Let's say recipe. Okay, the first thing you do is to identify the probability function or probability density of interest. The probability function refers to cases where we have a discrete random variable, and the probability density where we have a continuous random variable. And fortunately, this method is essentially identical for either one, for both discrete and continuous. Two. And we're going to call this little f of x as usual. And then to form the likelihood function, L, where L is equal to little f of x1 times little f of x2 little f of xn. Now, once you've formed that function, then calculate partial log of L partial theta, where theta is the parameter of interest, and then finally set that derivative that you've just calculated equal to 0 to find the estimate theta hat. So let's do a couple of problems and see how this goes. In your book, they've already done the normal distribution. So let's look at problem 25.2.3, which deals with the Poisson distribution. Now, you will recall that for the Poisson distribution, remember now, their first step is to identify the probability function or probability density. And in this case, since the Poisson distribution is a discrete random variable, we're talking about, it's called the probability function, and f of x is equal to mu to the x over x factorial times e to the minus mu and this is where x is equal to 0, 1, 2, dot, dot, dot. Now that's step 1 in our recipe. Number 2, we form the likelihood function L, where L is equal to f of x1 times f of x2 dot 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 f of xn. So L would be equal to mu to the x1 over x1 factorial times e to the minus mu times mu to the x2 over x2 factorial e to the minus mu dot 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 mu to the xn over xn factorial e to the minus mu. And that can be written a little more compactly. We can write this as mu to the x1 plus x2 plus dot 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 plus xn over x1 factorial x2 factorial dot 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 xn factorial, and then the only other thing we have to account for is e to the minus mu, which appears n times. So we have e to the minus n mu. And that completes step 2. And now for step 3, we want to calculate the derivative with respect to the theta of the log of L. And now they tell us in problem 3 that the parameter of interest is mu. So in problem 3, we want to find then partial log L, partial log L, partial mu. Well, let's go ahead and calculate that. So the log of L is simply equal to the log of this expression right here that's circled. And remember that the log of a product is the sum of the logs, and so we could write this as log of mu to the x1 plus dot 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 plus xn plus the log of e to the minus n mu minus the log of x1 factorial dot 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 xn factorial. And this could be written in a slightly more compact form, like this. We could write it as x1, natural log. We'll just leave the first term as it is, of mu to the x1 plus dot 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 plus xn. But for this second one, since we're taking the natural logarithm here, and this is the natural base, then this second term just becomes minus n mu. And then the last term I'll leave as it is. So natural log of x1 factorial dot 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 xn factorial. So this is the expression for the natural log of L, but remember now in step 3 we want to calculate the derivative of that with respect to the parameter of interest, and the parameter of interest here is mu. So we want to calculate partial log L partial mu. Okay, so when we differentiate this expression on the right-hand side with respect to mu, let's see what we get. Well, remember that the derivative of log of u, not mu now, but the derivative of log of u is 1 over u du dx. So when we differentiate this log of mu raised to this exponent, we're going to get 1 over mu raised to that exponent. So we'll get 1 over mu to the x1 plus dot 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 plus xn. That's 1 over u. And now we have to differentiate this with respect to mu. And when we differentiate this expression here with respect to mu, we're going to get x1 plus dot 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 plus xn mu raised to the x1 plus dot 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 plus xn minus 1. And that completes the process of taking the derivative of this first term with respect to mu. Now, taking the derivative of the second term with respect to mu is very easy. This is just minus n mu, and when we take the derivative of that with respect to mu, we just get minus n. And then taking the derivative of the last term with respect to mu is the easiest of all, because there's no mu there at all, so the derivative of that last term with respect to mu is 0. So this is our final answer for step 3. This is the derivative of the partial derivative of log L with respect to the parameter of interest, which in this case is mu. And now the final step of this process is to set that derivative equal to 0 to find mu hat. In other words, what we're saying here is that when mu is equal to mu hat, that's the choice of mu that will make this derivative expression equal to 0. So we get 1 over mu hat to the x1 plus dot 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 plus xn power multiplied by x1 plus dot 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 plus xn times mu hat to the x1 plus dot 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 plus xn minus 1 minus n is equal to 0. Again, when mu is equal to mu hat, this is just saying that when mu is equal to mu hat, then this expression is equal to 0. So that's what allows us to write this expression right here. Well, look at this for a moment. Here in the numerator we have mu hat to the x1 plus dot 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 plus xn minus 1, and here in the denominator we have mu hat to the x1 plus dot 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 plus xn. There's no minus 1 there. So if we have mu hat raised to the power minus 1 divided by mu hat raised to that power, well then that's just mu hat raised to the minus 1 power, or 1 over mu hat. So this is the same thing as x1 plus x2 plus dot 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 plus xn over mu hat minus n is equal to 0. And now if we interchange mu hat, well, if we just do a little bit of algebra, basically, what we will get is mu hat is equal to x1 plus x2 plus dot 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 plus xn over n. And that is our formula for estimating the parameter mu in this problem. So all we have to do is to adhere to this recipe, and it's, you know, it may be a slightly tedious procedure, but it's actually fairly straightforward. So now let's look at another example. Oops, I see actually there's a bit more to this problem, because now they want us to apply this formula that we've derived to a particular case. And the case of interest, they say apply it to the sample 10, 25, 26, 17, 10, and 4. So apply Okay, sorry for that difficulty. So here we say apply. Well, I'm still having a problem. Okay. Sorry about that. I'm having some technical difficulties. But they, to finish up problem 3, then it says apply it to the sample 10, 25, 26, 17, 10, 4, giving numbers of minutes with 0 to 10, 11 to 20, 21 to 30, 31 to 40, 41 to 50, and more than 50 flyers. Per minute. Respectively. Checking in at some airport check-in. Checking in at some airport check-in. So the sample is right here. These are our x1, x2, x3, x4, x5, and x6. And so therefore mu hat is 10 plus 25 plus 26 plus 17 plus 10 plus 4 over n, which is the number of samples that we have, which in this case is 6. And so this comes out to be 92 over 6, or 15.3 repeating. So now that completes problem 25.2.3. Now, and again, that was for the Poisson distribution, which is a discrete random variable. Now let's look at one for a continuous random variable. We'll do problem 25.2.11. In this case, it asks us find the maximum likelihood estimate of theta in the density little f of x is equal to theta e to the minus theta x if x is greater than or equal to 0 and little f of x equals 0 if x is less than 0. Now, as I mentioned already, even though this is a continuous distribution and the previous one was discrete, the method will go in exactly the same way. So we've already done step 1 here. We have identified the probability density, and now remember that step 2 is to form L. So we have L is equal to f of x1 times f of x2 dot 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 f of xn. And so this will give us L is equal to theta e to the minus theta x1 times theta e to the minus theta x2 dot 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 theta e to the minus theta xn. And that could be written more compactly in this way. We have n terms here, so we have n thetas multiplied together, so that will give us theta to the n power, and then we can combine all these exponential terms and have e to the minus theta times x1 plus x2 plus dot 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 plus xn. And that is a nice compact expression for the likelihood function in this case. Now remember that in step 3 we want to calculate partial log of L partial theta. So let's form log of L first, and then we'll take the derivative of that with respect to theta. So the log of L is equal to the log of this, and remember again that the log of a product is the sum of the logs. So we have the log of theta to the n plus the log of e to the minus theta times x1 plus x2 plus dot 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 plus xn. Now we want to take the derivative, the partial derivative of that with respect to theta. And so what do we get? Well, as was the case in the previous problem, the first thing we need to remember is the expression for the derivative of the log of u. And that's 1 over u times du dx, or in this case du d theta. So we have 1 over this, that's 1 over theta to the n. And then we have to differentiate theta to the n with respect to theta. And so that's n theta to the n minus 1. And this is the derivative of the first term with respect to theta. Now, this second term, actually, let me note up here that we could write this in even nicer form. This is a log, the natural log of the natural base to this power, so this is just minus theta to the x1 plus dot 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 plus xn. And so now, okay, this term right here, as we've already said, that's the derivative of the first term, and the derivative of the second term with respect to theta is trivial. The derivative of minus theta multiplied that by this with respect to theta is just minus of that. So we have minus x1 plus x2 plus dot 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 plus xn. And that completes step 3, which is finding the partial derivative with respect to theta of the logarithm of the likelihood function. And now remember that the final step is to find theta hat by replacing theta with theta hat and setting this equal to 0. So we have 1 over theta hat to the nth power times n times theta hat to the n minus 1 power minus x1 plus dot 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 plus xn, and that is now equal to 0 since we've replaced, or we're evaluating theta at theta hat. Okay, and now again we just do a little bit of algebra. This becomes n over theta hat and we can take this term with the x's over to the other side, is equal to x1 plus x2 plus dot 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 plus xn, and we finally get then that theta hat is equal to n over x1 plus x2 plus dot 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 plus xn. And that completes problem 25.2.11. So as I say, this is a really, once you get the hang of it, I think that this is a straightforward procedure. And so now let's look at a couple of problems using this procedure. Okay, so now we will look at problems for this section. The first one, B17-1, is very similar to problem 25.2.5. And what you are asked to do is to find the maximum likelihood estimate of P in the probability function f of x equals P to the x times 1 minus P to the 1 minus x for x equals 0 or 1, and f of x equals 0 otherwise. And the choices are A, the log of the quantity x1 plus x2 plus dot 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 plus xn divided by n. B, n times the quantity x1 plus x2 plus dot 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 plus xn. C, n over x1 plus x2 plus dot 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 plus xn. Or finally D, x1 plus x2 plus dot 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 plus xn over n. And problem B17-2, find the maximum likelihood estimate of theta in the density f of x equals theta squared e to the minus theta x if x is greater than or equal to 0, and f of x equals 0 if x is less than 0. And the choices here are A, x1 plus x2 plus dot 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 plus xn over n and all of that squared, or B, n divided by 2 times the quantity x1 plus x2 plus dot 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 plus xn. C, n over the quantity x1 plus x2 plus dot 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 plus xn, all of that squared. Or finally D, 2n divided by x1 plus x2 plus dot 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 plus xn. So those are the two lecture problems, and then there will be other problems in class. And be prepared, we might have a problem or two of a review nature. In other words, about some of our past lectures. So that concludes it for lecture B17, and good luck.